Hello, 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 and welcome back to another episode of Kerbal Space Programming. Kevin here, and we are starting off on a new adventure, which is to get ourselves a station in low Kerbal orbit, because we've unlocked a bunch of stuff now that Gregory Kerman has successfully returned, including docking ports and monopropellant, which is going to open up brand new avenues of lots of things. But before we start doing that, we need to actually figure out how to control these new things with KOS. And to do that, we need to talk about vectors. Now, because vectors, at least in my memory, weren't really covered until maybe if you took calculus in high school, it kind of didn't happen. We're going to briefly touch on what they are in case you're not familiar. So I'm going to hit a key. I've loaded up a script already, and this is a vector. Well, these are three vectors. One of these is the top vector, one of these is the forward vector, and one of these is the starboard vector. So we've got top and bottom, forward and backward or aft, and then starboard and port. But, we can think of these as top, down, left, right, etc., etc. And these are directions that we can get about the current ship. So the vector itself is nothing more than a direction and a magnitude, which is the length of this vector. So for our top vector, it is pointing in the direction that is to the top of our craft, assuming that this is the forward, that this red one is the forward direction of our craft, and this is the starboard direction. And we can have different lengths here, and I'm going to hit the RCS button. There we go. And now we have vectors of a larger magnitude, right? So basically everything that we've done up until now has largely been based on orbital systems, right? We're talking about maneuvering by increasing our apoapsis, decreasing our paraapsis, that sort of thing. Now we're going to actually have to talk about 3D space, because we're talking about a very small area when we're talking about things like docking. So what we want to start doing is figure out how we can control RCS using this sort of 3D space. And the first thing that we want to talk about is what does KOS actually let us do as far as control. So I'm going to pop this up here, and I'm going to say set, come on. Oh, because the program is running. There we go. Set ship controls 4, 2, 1. Is that it? Nope. Is it ship control? There we go. Okay. Now, that's not doing anything because the RCS is off. Let's turn the RCS on. And there we go. We can see that these are firing, and it's trying to set the 4 to 1, which is 4 to 1. Okay, yeah, could have picked a better name, but, or rather, I could have picked a different direction to start off with. Let's go ahead and set it to -1. Okay. That's good old hull cam being weird. Okay, we did set it, but it looks like, yeah, and you can see there are little tufts coming out of here, but it's getting cut off by the monopropellant. Let's set that to 0. Let's, come on. Oops, there are 2 periods there. Let's change this and set star to 1. What? What? Let's, okay, forward, back, starboard. There we go, starboard. Okay. And now you can see it's trying to push us in the direction of that starboard vector with the number 1. So we can set these to between 1 and -1, and it will fire the RCS in that direction. Now let's jump over and take a look at the script so that we can see kind of how we created these vectors, and we can start looking at how we can start controlling the ship using RCS. Alrighty, so this is the program that we just ran that I had already loaded up before you joined the episode. So we start off with on SAS, which is going to fire when SAS is turned on or off. And this is, don't be confused because it's on. It's not turning SAS on. I believe you can say SAS on, which is also valid syntax, which would turn on the SAS. But instead we're saying on SAS, which means track what SAS is, and then if it changes, go ahead and fire stuff. The first thing we're going to do is we're going to say clear vec draws. This is something that comes with KOS. If we've drawn vectors to the screen, then go ahead and get rid of all of them. That way, if we want to add new ones, everything else is already cleared off. And there's another function that we get from KOS called vec draw. Now this accepts a bunch of arguments. It's kind of like the notify stuff that we were writing, so that we can throw up text to the screen. Now the first argument that we're going to pass is a vector, and this is what a vector looks like in KOS. We're passing it in 3 coordinates, so we're saying the x component of the vector, and the y component of the vector, and there we go, x, y, z, and the z component. So what those actually happen to be, we don't necessarily care too much about. because we'll generally be getting vectors relative to other vectors or relative to the ship. So we don't necessarily care what axis we're dealing with. But that's kind of a way that you represent vectors, that you say, okay, something is moving 2 in the x direction and 3 in the y direction and, 1 in the z direction or whatever. The first vector we're passing is where the vector should start, and we're saying we want it to start at 0, 0, 0, so this absolute center of the ship. Now we're going to say the end point, which is this ship facing 4 vector. This is something that, again, we get from KOS, because we're just trying to determine where is the 4, which way is 4, and that's what that is. And we pass in an RGB value just to color it, and we can give it a little string, which gives it the little text. And then we can also scale up the vector when we're writing it out so that it makes it easier to see. And then this final variable is whether or not it should be shown immediately, because you can create vectors and then have them be invisible, so you can turn them on and off. But we're just going to go ahead and set it to true. We're going to do the same thing with star vector, which is our starboard vector, and top vector. So we're drawing all 3 of those, and then we're going to call preserve. That way that this body will continue to operate even after the first time that we've called SAS. Now, any time that we call SAS, it's going to go ahead and run this function. And then down here on RCS, we're doing the same thing, and I cheated a little bit because I mentioned that vectors can have different magnitudes. I wasn't actually changing the magnitude. I could just go here and say, times 10 or whatever, but instead I just said, let's scale this up by a factor of 10 down here in the argument. And this is exactly the same as what we did with SAS, and we preserved that too. And then finally we just said, and wait until false. And of course, false is never going to be true, so this program will never terminate. That way these on blocks can continue to operate. If we didn't do that, then the program would go through and it would say, okay, I'm going to wait to see if you hit SAS, I'm going to wait to see if you hit RCS, and then, oh look, the program's done. I guess I will shut down. Bye. And then those blocks wouldn't run anymore, so we needed to make sure that the program continued to run until we were ready to be done with it. Now that's cool and all, but what does it really matter as far as these vectors? As we saw, we can set these things by saying set ship control 4 to something. Wow, something. And set starboard and set top to something, right? That we're not setting them to vectors, we're setting them to a value between -1 and 1. So why do we care about these vectors? Well, what we want to be able to do, because we're going to be playing with vectors a lot in terms of figuring out what is our velocity relative to the target's velocity, what is the vector that points us toward the docking port on the ship, what is a whole bunch of stuff. What we really want to be able to do is, instead of setting all of these controls, figuring out the -1 to 1 value for all 3 of these, it'd be great to just say, let's throw a vector at a function and have it go ahead and figure out what those values should be. So instead of saying, set us to go up a little bit, and set us to go to the left a little bit, and set us to go forward a little bit, say, here's the direction, then you figure out how much force it should be in all 3 axes. Now, of course, to do that, though, we need to figure out what these somethings actually are relative to the vector. So we could call this by saying translate, and then we'd create a vector of 5, 2, 1, whatever we choose. And then this should figure out what these somethings are and set the controls appropriately. So let's figure out how we can go from a vector that is in this 3D space to figuring out what the components should actually be for our RCS. So where better to find out that information than on Wikipedia? So I'm here on the scalar projection wiki page, where we can find some complicated math, not too complicated, it's fairly easy, regarding these vectors, and how we can figure out, given a vector that is pointed in any direction, how can we figure out what amount of that applies to the vector that aligns with the axis that we're trying to control? Because we saw, when we drew them out, that we have a vector. We have like a 4 vector that's pointed only in the direction that RCS would translate. So it would translate forward or backward, right? So what we want to figure out is that for a vector A, and this is actually a good diagram, so we've got this vector A that's going up here. We don't particularly care about A. What we care about is how much of A exists in B. You can think of it as if A were hovering on top of B, how much of a shadow would it cast on B? Or just how much of this component exists? And we've got a couple of different ways of figuring that out. It says a scalar component. It gives us two ways to do that. We can find the magnitude of A. This means magnitude. And then multiply it by the cosine of the angle. And no, we're not going to do that. What we can do is we can take the dot product between A and the unit vector of B. Now, unit vector sounds complicated. It's not too complicated. All it means is that we're going to take B and shrink it down so that its total length is 1. And it just so happens that the 4 vector and star vector and top vector that we get from KOS are already unit vectors. They already have a length of 1, so we don't even need to worry about that. We're just going to take the dot product of these two vectors. Now, you don't need to worry too much about what a dot product actually is. There are kind of two ways to multiply vectors. One of them gives you another vector, and one of them gives you a number. The dot product gives you a number. The cross product gives you a vector. And we don't need to worry too much about the math of how those work because KOS actually has that stuff built in. We will be using both of those, but for now, we're just going to say, okay, so we need to go ahead and multiply A, which is the target vector that's pointing in the direction that we want to go, and then take the dot product of that with the direction that our RCS can control. So if we're trying to figure out what our I should stop using 4. If we're trying to figure out what our top should be, we're going to say take the target vector and multiply it by the top, and we'll know, okay, that's how much of the target vector is in the direction that we're controlling right now. So this actually makes things pretty simple for us. I'm going to go ahead and delete this. I'm going to say vector times ship facing 4 vector. And that is all we need to do, right? We're taking that dot product of the direction that we want to go and then multiplying it by the 4 vector, which is the direction that of the control that we're actually analyzing. And we can do the same for the remaining 2. And we can do the same for the remaining 2 items. Now, there is one small thing that we have to worry about, and that is that what if this value ends up to be greater than 1 or less than -1? Well, then we've got a problem because our controls need to be set to a value between those regions. So what I'm instead going to do is I'm going to take our starting vector and I'm going to say, let's grab the unit vector. Let's make sure that the length of the direction that you want us to point in is also 1. Because if you imagine that we said, I want to go 500 to the left. And we said, okay, well, let's figure out how much of that direction lies on the left. Oh, look, it's 500. Well, that's not good. So we're going to scale it down so that the maximum length is 1, regardless of the direction. So we'll go ahead and say set vector to vector normalized. And this is something that we get from KOS. It's part of what vectors are, and it'll automatically go ahead and scale that down to a nice unit vector. And now we know that these things are nice and safe. I'm just tidying this stuff up here because there we go. All right, that makes me feel better. So let's think about actually testing this out. I'm going to go ahead and open up the vecdraw so I can copy this in here. Actually, let's copy all of this. And yeah, we'll just leave that there for the moment. I want to test out this function that we've created just so that we can see if it happens to work. So we're going to say RCS on, turn on our RCS, and we'll turn the RCS, well, we'll not even worry about that at the moment. So what we want to do is we want to test that the RCS jets are going to fire in the direction that we kind of expect for a whole bunch of different vectors. That way we can make sure that this function works. So I'm going to say for x in list -1, 0, 1, and for y in the same, and for z there. So now all I'm doing is I'm just saying, let's go ahead and run over all of these elements and create a bunch of vectors. I'm going to go ahead and say local test vector is v. Remember, that's how we create a vector. We're going to pass in x, y, and z. And now we'll go ahead and paste this stuff in. And just indent that. There we go. We'll clear what's been drawn. We'll say go ahead and instead of the for vector, we want to actually draw the test vector. And we'll leave the color as it is. Oops. Test vector. And now we can actually call our function. So we'll say translate test vector. Right. So there we go. We're going to go through and say for all of these different versions, -1, 0, 1. So we're not testing the full range of possibilities, but we're testing a bunch of them. I think there are 27 in all, right? Because we've got 3 times 3 times 3. And we're creating a new vector for each of these. And we're going to say clear the vector, draw the vector that draw the direction that we want to point in, and then try to RCS in that direction if you can. The last thing we're going to do is we're going to go ahead and say weight. Let's make it 10. There we go. That way it won't rapidly switch between all of these vectors. So I'm going to go ahead and copy this over, and then we can take a look and see if it works on the Launchpad. And back on the Launchpad, we are ready to run vector test 2. Are you ready? Let's do it. Oops. Nope. We are not on the archive volume. Switch to 0. And then run vector test 2. And there we go. We can see it's drawing the vector that is the random direction that it first chose. And we can see this makes sense if we look at the way that the jets are firing. We can see the emissions coming out of here. It's trying to push us out, and it's trying to push us up a little bit, and it's trying to push us that way a little bit. That makes sense. Okay, so one vector, we're good. Let's see if it can advance to the next one. There, okay. Not much of a change, but still seems to be firing in the correct direction. We're not seeing it. We're not seeing those particles trying to adjust us too much in that direction. I suspect there's still a little bit coming out. Oh, there we go. Another one. Yeah, the unfortunate thing is when we're getting down to very small amounts, there's very little particle effects that we can see. There's a tiny, tiny little bit coming out there, and now there's a lot more. So, okay, it's picking all of these random directions, and it looks like the RCS jets are firing in a way that would put us in that direction, which is fantastic. Yeah, if we can see, there's just a tiny little bit coming out here. Alrighty, so I'm going to go ahead and call this function a success, which is great because that means we can move on and start thinking about how we can use this beyond just saying, here's the direction, go in that direction. Okay, so since we are running a little bit low on time, I've gone ahead and written a script that's going to use this translate function that we've designed. All right, we're going to put a ship up into orbit, and we are going to have it detach and then try and dock with itself very carefully. All right, so it's first off going to stage and then wait 10 seconds. So I've got a stack separator. It's going to go ahead and drift its way off for 10 seconds. It's not going to get too far away because we're not worrying about that yet. But we're going to list the docking ports in docking ports. We've seen things like listing files and listing parts. This is just another mechanism that we can get so we can find all of the docking ports. I'm going to set the docking port, the one that we're using, to the first one that it gets, so index 0, and we're going to say control from that docking port, please. Next, we have to find the target port, the port that we are trying to dock with, so I'm going to set it to false, and then I'm going to list all the available targets, and I'm going to say for every target, if that target has a docking port, and that docking port's tag is docking port B, which I've gone in and tagged it as docking port B, then go ahead and set the target port to that docking port. So this is a way that we can look and make sure that we're trying to dock with the correct ship and the correct port on that ship. So the first thing that we want to do is we want to cancel our relative velocity. So I'm going to turn on RCS, and I'm going to lock relative velocity to our ship's velocity, our orbital velocity, minus the target port's ship's orbital velocity. Now this is important because if we look at our orbital velocity, it's going to be a very big vector because we're traveling around Kerbal, right? What we care about is what our velocity is relative to the target. It's kind of like if you're walking on a train and the train is moving 50 miles an hour, we don't care that we're moving 50 miles an hour. We want to know that we're moving the 1 meter per, I don't know, however fast people walk. So we can subtract the vector of the target from our own and figure out, okay, well, we're only moving 1 meter a second, 2 meters a second, whatever, relative. I'm going to say until the magnitude, the length of our relative velocity is less than 0.1, let's translate in the opposite direction to what our relative velocity is. So if we're traveling in the x direction by 5 and the y direction by 6 and the z direction by 7, well, then we're going to translate to -5, -6, -7. And then once we're done with that, we'll say translate to 0, 0, 0, which is going to turn the controls back off. Now we need to align for docking. We're going to lock our steering to the opposite of the target port's port-facing vector. Now this is something that we get from KOS. It's part of the docking port part. You can actually determine, okay, what is the outward-facing vector. So it would be an arrow that points exactly outward from the docking port. We want the opposite of that because we want to point directly at the docking port. So we're just going to lock the steering to the opposite of that. And then finally we move on to docking. All right, so we'll lock our docking vector to the target port's node position, which is the part of the docking port that actually docks. We don't care where the middle of the part actually is. We care where the docking part of the part is. So we're going to say our docking vector is the target's position minus our own docking port's position. And then we're going to say until our docking port state is not ready. So the state is ready when it's totally ready to dock, and it'll change to docked at the point where it's actually docked. So we're going to say until that's true, we're going to translate some more. Now what I've done here is I've said we're going to take the docking vector, which is that difference in position. We're going to normalize it because we don't want to approach it really, really fast. We want to approach it at about 1 meter per second. And that's normalizing, is taking the vector and making it a length of 1. And then we're going to subtract out the relative velocity. If we didn't do this, then every time we called this, it would say, okay, well, we're going to fire the RCS with a length of 1. And our speed would gradually build up. So we're going to subtract out the relative velocity so that we only end up with that 1. And there we go. We're going to translate to 0, 0, 0, which will turn off our RCS, and then we'll actually turn off the RCS and we will print done. Alrighty, so let's jump over and see how it goes. Alrighty, so here we are with our little craft, which I've uploaded the instructions to. You see it's got all these parts. It's got a decoupler in front of a docking port. So this whole thing should come off as soon as it receives its instructions. It should fire off and then try and dock with the remainder of this craft. So it's going to fire off and wait. There we go. It's going to fire off and then wait 10 seconds and then try and find its way back. Hopefully. We'll see. Okay, there we go. It says canceling relative velocity and aligning for docking and docking. All right. Good, good, good. And yeah, I can even set this as the target. And okay, you see it's trying to keep the target speed at 1, but it's also firing the RCS at a speed of 1, which is probably not the best. There's a lot of tuning that we could do to make this better, but and okay, I guess it's the rotation of this thing because it's not powered, but okay, you can do it. You can do all right. There we go. We have successfully redocked with a craft in orbit, preparing the way for future orbital rendezvous and dockings, which we will explore in future episodes with hopefully less wobbliness and weird side translation and that sort of thing. But that will all have to be in the next few episodes, so I will hope to see you then. Cheers.